till now, we basically have studied atmospheric neutrino problem and its solution and things that came with it. All this formalism of mixing, thermal mixing, constant density, blah blah. So now let's go to the second big problem that neutrino physics tackled over the last 50 years. The problem was discovered in the 60s, and the solution actually was confirmed only maybe 5 years ago. So it actually took more than 40 years for the problem to be solved. So let's try to understand first what the problem was, and let's try to see how we progressed over its solution. So to understand the problem, let's go in 3 stages. So first we talk about neutrinos from the sun, what kind of reactions take place. Then we talk about the measurements of solar neutrinos. Measurements will show you that there was some discrepancy. And then we will try to look at what happens to neutrinos when they travel to varying matter density. So today, let's see how far I will reach, and the rest of the things we will do. So let's first look at neutrinos from the sun. So it's good to have a picture of the sun in mind. Sun is not a homogeneous object, but consists of many layers. So this is the so-called chromosphere, which is basically essentially what we see, the outer part, the corona and so on. Inside that is the so-called convective zone, radiative zone, and the core. What we are interested in is the core. Because neutrinos are produced mainly inside the core. Okay. It's kind of obvious because neutrinos are produced through nuclear reactions, through fusion, hydrogen fuses from helium. In sense. So nuclear reactions definitely are much more in number near the core. So most of the neutrinos will come from the core. Of course, some will have some kind of a layered structure. So the outside layers will have more hydrogen, inside will have more helium, and there will be some heavy element like beryllium and boron. So as you go inside, so depending on what kind of nuclear physics cycle is there, at different densities, you will get different neutrinos. So we'll come to that and look at details of this. The thing to note is that it's only within the innermost 10% of the sun, 10% radius, that neutrinos are produced. Okay, outside that, the neutrino production is almost zero. Okay, so for all practical purposes, you can take the core of the sun, which is basically 1 in 1,000 volume. It's not 10 radius. That's where the neutrinos are produced. The density at that point is about 150 grams per cc. It's rather high. However, that is not enough to trap the neutrinos. Remember, we had done this small calculation. We did the homework, I don't know whether you did or not. But I had given this order of magnitude. If you take neutrinos from the sun, you make them pass through lead, which is less than 10 grams per cc, you will have to have a lead thickness of the order of lightness. Now we don't have lead, but we have density of the order of 150 grams per cc, maybe 10 times that. So no, 1 light year might become 1/10 light year, still much larger than the sun's size. Therefore, neutrinos, when they are produced, simply come out. So the sun's atmosphere, or the sun's mental core, offers no resistance to neutrinos. So these neutrinos will never be in thermal equilibrium inside the sun. So if you go inside the sun, okay, the temperature is of the order of Ke, kilo electron. Neutrinos that are produced are of the order of mega electron. Okay, this is not really anything to be surprised at, because neutrinos that come out don't interact at all. The nuclear reaction happens, neutrino gets produced, it just comes out. That's it. So immediately it will come to the Earth. So one way to look at it is, so basically when we look at the sun in neutrinos, we are looking at the core of the sun directly, and it was about 8 minutes ago. So it takes 8 minutes for them to come from the sun. On the other hand, if you want to get information about the sun's core from the light that comes out, the light, the photon produced in the core, while it comes out, will undergo many collisions. Okay. and by the time it reaches here, it usually takes something of a million years. Okay, so in some sense, neutrinos give us direct access to the core of the sun, as it was 8 minutes ago, not million years ago. The sun that you see is due to nuclear reactions that took place a million years ago. In fact, this was one of the major considerations when people talked about the solar neutrino problem. People thought, oh, in the night we see a sun which is million years ago, but neutrinos we see a sun 8 minutes ago. So maybe the luminosity of sun has gone down in the factor of 2. So such questions are the ones we should ask and we should be sure of. So this is just to give you a general idea of the sun. So essentially what happens is inside the sun you get hydrogen fusing into helium effectively. So each of these fusion in principle will give you helium plus 2 electron neutrinos plus light. So all the neutrinos that are produced are electron neutrinos. Some will not produce electron antineutrinos, it will not produce muon neutrinos or tau neutrinos. It will only produce electron neutrinos. So it's a pure UV source. It's not like atmospheric neutrinos where you have to figure out whether this was muon or electron. No, you looked at Chelan covering, how fuzzy it was, E-like, mu-like. Here, nothing of that sort. There are other problems, but we'll come to that later. At least we know that if something comes from the sun, it is always a new. Okay? If it is not new, it is some new physics. Okay? But new physics comes later. So standard model will mean that there is only news that coming out of this. So this was a very naive picture. This is a reaction that we see in textbooks, maybe even in school. However, things are not as simple as that. We should be careful and try to look at exactly what are the reactions that take place inside the sun, which will give us. So here is the chart. So what happens inside the sun? The main reaction is, so the first step of the reaction is 2 protons combining to form the deuterium, positron, and UV comes out. So this is a reaction that takes place almost 100% of times. Okay, because finally, initially, PP has to have to fuse. Okay. A very small fraction of times, this PP also fuse with an electron. And then you again get deuterium plus mu, but in this case, you do not have this positron again. When you emit a positron, it will always combine with some electron and annihilate it. But initial reaction is always this. Now this reaction has a threshold of 0.42 MeV, very low energy, and across 100% of time. This is slightly higher energy. So neutrinos that come from PP and PEP are in general low energy neutrinos. So in next slides they will be referred to as, we call them PP neutrinos and PEP neutrinos. Just the names. Now, so both of these, as you notice, have formed deuterium. This deuterium combines with another hydrogen nucleus to give you helium-3 and gamma. This gamma is very often just absorbed in the sun due to energy imbalance. So sun's density is very large. So this is not a gamma that we see. After this process, you can have 3 different reactions. This happens about 85% of times, this happens 15% of times, and this happens for the remaining very small fraction. See, this reaction has not given any neutrinos, it's given gamma. There are no neutrinos. Now this reaction, 85% of times you get 3 helium plus 3 helium, giving you 4 helium plus 2 protons. No neutrinos, that's fine. The cycle ends here. You get 4 helium and then so you get 4 helium and cycle essentially stops.
Those figures, they're not threshold, they seem to be the energy of the outgoing neutrino. Because in the 2 bodies.
Oh, sorry, I'm sorry. Yeah, sorry. Not threshold. Sorry, the energy of the neutrinos is less than 0.42 MeV. Yeah. Okay. And this is this neutrino has a fixed energy of 1.44. Okay. Okay, so 85% of times here you get 4 helium without neutrino, so that's okay. A small fraction of times you get what are called as HEP neutrinos. HEP simply means that helium and proton. He for helium. Here you get electron neutrinos, which are energies less than 18.8 MeV. So rather high energy. 15% of times, actually you get beryllium. Okay. Plus again a gamma, which we don't see. Now once beryllium is formed, it can do various things. It can either combine with electron, make lithium and give out mu. Or it can combine with electron. Okay, so it actually can give out mu, but at 2 different energies. So this will just essentially have electron capture from one of its shells and give you these 2. Or this beryllium can make a boron, and this boron again decays to 8 beryllium and gives out a mu. So notice that in all these processes, actually there are nuis emitted from many sources. These are called as PP neutrinos. These are PEP neutrinos. Then these are beryllium neutrinos. These are also beryllium neutrinos. These are called boron neutrinos. And these are called HEP neutrinos. Now if you go into all these details, you will see that every time what is emitted is nu and not nu bar. Okay. So, but this argument is not very simple. There is no simple argument to say, oh, we will always think. Just so happens that in all the reactions that we see here, it turns out that nuclear physics tells you that you get nu. It would be possible to imagine convoluted cases where you get nu bar. Just so happens that energy levels of nuclei, etc., are so that you don't get this. So, in some sense, it is a coincidence, good coincidence that you only get 2 these. And finally, you get every reaction stops at forming helium. So, if you go in any of these routes and you finally get your helium, you see that effectively the reaction looks like this, almost. Okay. But it can go through many things. All these neutrinos have different energies. That's very crucial when you talk about experimental. So these are very low energy neutrinos. See, this is less than 0.4 MeV. These are small energy, 0.3 MeV and 0.8 MeV. Then we get these ones which are 1.4. Then you have boron, which is a big spectrum, which goes up to 50 MeV. And then you have got an HEP, which have a spectrum which goes to about 90 MeV. So if you look at different energy regimes of neutrinos, we are going to look at neutrinos coming from different sources. So it's important to have an energy calibration to tell you which neutrinos these are. So this is approximately what the spectra of neutrinos. So you see, we saw that the main reaction that always happens is PP. Therefore, the PP spectrum is always dominated. So,
the neutrino images spread out through a region.
yes.
We are saying that this energy and that is the highest energy.
No. So, let's look at this. Whenever the energy given is only a number, it is a monochromatic neutrino, single energy. Okay. Whenever it says less than something, it is the energy of it. You have a spread below the energy.
So when the neutrino is directly produced to be an electron, it will be spread out because of the electrons.
Yes.
So then it is always less than 1. But otherwise it will be a fixed state.
So you see here, whenever the final state is 2 body, you have monoenergetic neutrino, right? So here, final state is 2 body, so energy is single. Here is 2 body, here is 2 body, so it's single. Here is 3 body, so there is a range of energies. This is a 3 body, so the range of energies. This is 3 body, so this is the range of energies. So it's very straightforward. 2 body final state, monochromatic. 3 body final state, you get a range. So, This is what a spectra look like. So these lines that you see are monoenergetic. This is beryllium 7 line. This is another beryllium 7 line. This is the PEP neutrino line. This is the PP flux, which is the most dominating. Note that this is the logarithmic scale. So this PP neutrinos form more than 99% of the neutrinos. Then we have got this boron neutrinos, this flux, which goes up to about 50 MeV. And then we have got this HEP neutrino flux, which goes up to 90 MeV. So when you look at a neutrino, there's nothing that tells you whether it came from in principle beryllium or boron or HEP. It's energy that gives us some idea. Sometimes it's very clear. So if the neutrino is here, for example, it's very clear it is a HEP neutrino. But if it is here, it in principle is a mixture of boron and HEP. However, note that in this region, the boron flux is about at least 100 times more than HEP flux. So in this region, you can actually neglect HEP flux. That's what people do. People go to a region where one of the neutrinos dominates, which is the instances where the neutrinos came from. So the shapes of these spectra are very well known because we know weak interactions very well. Therefore, we can compute the final spectra function of energy. So therefore, if you give me a weak interaction like this for example, ask me to calculate the spectrum of this nu E, you can do it. In fact, although all of you have done one field theory course, or have done calculation of one Feynman diagram, should be able to do this. This is it's a very straightforward spectrum of electrons. It's just like beta decay spectrum. So the shape of the spectra are not in doubt. They are perfectly well known. What is not well known is the total flux. So this flux, for example, boron flux, can change by about 20% up or down. You can see this number. That's not well known. And that is because the extent to which these nuclear reactions happen depend a lot on the internal conditions inside the sun. So they depend on what is the temperature inside and so on. And a small change in temperature can actually cause a large change in the sum of one of the reactions. And we saw earlier that we had about 10 different reactions, all of them coupled with one another. And therefore there is a cascading effect. So it's not very easy to say what the actual flux is. There is something called as SSM, or Standard Solar Model, which predicts certain fluxes. But as we saw, those fluxes are uncertain to some extent. So this boron flux is uncertain to about 20%. This PP flux is known to of the order of 1% because it is just like the energy of the sun, measured light. We know that every neutrino that came to us started as a PP collision. So therefore, once we know how much light the sun gives out, we know how many PP neutrinos actually. So this is very certain, but all of these are very uncertain. 10%. This is very well known, 1.5%, because this is the initial energy reaction. That's very well known. And these are again known to with very low precision. The HEP precision is in fact much smaller. So when you want to look at solar neutrinos, we have to take into account that we are going to measure all these kinds of neutrinos. Then we go towards asking ourselves as to how we will measure this. And as I mentioned to you before, neutrino physics, the main discoveries have often been made by nuclear physics people or chemists. So you will see here that I have got this dark green band, dark blue band, light blue band, and much lighter. What it shows is three kinds of experiments. The experiments that, so this is a familiar thing, right? This is super K. If you see the super K, this band tells you what super K is sensitive to, and that is energy is more than 5 MeV, which means only boron and HEP fluxes, nothing less than. SNO is Sudbury Neutrino Observatory. We will come to what it does. Then there are experiments which involve chlorine. Those experiments are sensitive to energies more than about 0.9 MeV, all the way to highest energy. So if you have an experiment in chlorine, that will take into account these beryllium neutrinos, PEP, boron and Hep neutrinos. And if you have an experiment which has gallium, that can be sensitive to everything. So you can look at PP, beryllium, PEP, boron and Hep. So in some sense, gallium is the most. The reason you haven't heard much of gallium and chlorine experiments is because these experiments cannot measure the energy of neutrino. So I'll show you what reaction is. You will see that it's not possible to determine energy of neutrino by using chlorine and gallium. Therefore, they have only a limited sensitivity. All you do is measure number of neutrinos above certain energy. That's it. Okay, whereas if you look at super K can give you a spectrum. Okay, so you can look at how the flux changes as a function of energy. That's a lot of information. That is something you will get. So this is essentially how we expect the sun to be. Okay, let me just mention SNO. So super conductor uses water. It's a water cylinder. SNO uses heavy water. So D2, not H2. That's the only difference. Instead of hydrogen, it is deuterium. And we will see how that helps. And again, the threshold of SNO is also 5 MeV. So both of these essentially look at boron neutrinos. Hep is very, very small. Okay. So with this theory, now let's try to look at what the measurements look like. So let's first look at what are called as radiochemical experiments, which are the chlorine and the gallium experiments. So the first experiment was the chlorine experiment done by Davis. This was the first one that detected solar neutrinos. That's why he got Nobel Prize in 2001 or 2. So this was done in the Homestake mine in South Dakota, US. And when the experiment was okay, let's see what the experiment was. The experiment was UVs come. They combine with chlorine. Okay. Now this chlorine was actually used as cadmium chloride, which is a cleaning fluid. It's a detergent. So this was in some sense cheap experiment. It was not really cheap because it was almost 400 tons of this cleaning fluid. Okay. Small by current standard, but large by those standards. So there were 400 tons of cleaning fluid. This is cadmium chloride. So this is chlorine. Now, UV combines with this chlorine, interacts, it converts the chlorine to argon, gives out an electron. This electron has a very low energy, 0.8 MeV. Okay. It gets lost. No Cherenkov. That was not a type of Cherenkov. In maybe Cherenkov, you can't look at a neutrino which is 0.8 MeV. You need to have at least about 5 MeV of energy to look at the Cherenkov line is the intent. Okay. So this is a very different kind of experiment. It's not that you see a reaction and you see electron going out and you see how okay, neutrino came. Electron not the way this one. This electron is lost. Only thing you can look at is this argon. Now how do you look at this argon? This argon is radioactive. It is radioactive. Its lifetime observed a few months. Observed let's say 1 month. So what was done was this tank was just kept in the mine for about a month, some 22 days. I forget what exact cycle is. After about a month, you take out all these 400 tons of fluid, pump it out, and literally count the number of argon atoms inside. So it's a very extremely sensitive experiment. There were methods of actually counting argon atoms. And you can imagine the rate of neutrino interactions here would be, it's only 400 tons. Okay? So a few atoms, one interaction, a few days. So in a month, you would get upward of 10 neutrino reactions. So now you have this 400 tons of fluid. You take it out, and from these 400 tons, you count number of argon atoms of the order of 10. And the genius of Davis was that he actually managed to do this without losing any of these atoms. Okay. Therefore, this is a very sort of revolutionary experiment. It really required very high precision. Almost no up the order of precision that you need an LHC when you have collisions and you figure out which are the particles. So we have 10 atoms out of 400 tons of fluids. That is kind of mind-boggling. What he did, and he was very confident that he actually measured every argon atom. So then one would say that if you do that, you will observe exactly what you expect from the sun. Instead that you did not, what you observe is something like this. So data you had by the standard solar model, so expectation was about 1/3. Okay, errors are other small. So these are current errors. That time errors were maybe 10%, 15%. But this is what Longstreet data currently is, about 1/3. So which told us that out of the image that we expect from the sun, 1/3 have been lost. I'm sorry, 2/3 have been lost. Only 1/3 have been lost. Okay. So of course, first thing to do is suspect the experiment for this. He said he will measure all the argon atoms, maybe just miss some argon atoms. Some of people were convinced of this. They must have done calibration by introducing randomly just 10 argon atoms in some fluid and then giving to Davis and asking him to count from the continental examples. But I don't know the history, but nothing to check. Right? This was checked. People were convinced that he measured the number of atoms very exactly. So therefore, experiment is not a problem. Next problem is astrophysics. You don't understand the sun. Okay, it's a complicated thing. And therefore, why do we trust it? This question of astrophysics actually stayed on till 2002. Still continues. All the experiments I will mention should be looked in this diagram. People are suspecting, why should neutrinos have mass? Astrophysicists haven't calculated things correctly, so why should we believe? So chlorine experiment, therefore, gave us this factor of 1/4. Next experiments, there are so-called gallium experiments. And now people wanted to check each other's results. So there were 3 gallium experiments. So there was this experiment called as SAGE, another called as Galax, and a third called as GA. The gallium experiments are very similar. Again, you had UV. When they interact with gallium, they form germanium. This germanium is radioactive, so it decays, and you count the number of germanium. So very similar method. So these are not online experiments, they are also called offline experiments. You do them for 1 month, take the fluid away somewhere, and you count the number of atoms. The energy threshold here is much lower, 0.233, so they can actually also measure the peaking. So now all these 3 experiments measured neutrino fluxes. And again you can see the observations. About 60%, 60%, about 50%. Okay, within errors. Errors are not of so it's between 50 to 60%. So again, neutrinos seem to be lost. However, the fraction is very different. Fluorine people only found 1/3. Gallium people found 60%. So another question is why do people find different? Not very surprising because we know that energy they are sensitive to are very different. So gallium, fluorine only measures this. Gallium also measures this. Okay. So it's possible that in this region you only save about 33%, and in this region you save a lot more. So you get a lot of 60%. That's quite possible. So that's what it is. So these were radiochemical experiments.
So, how do you know how many number of neutrinos are being produced at sun? I mean, I have an expected number of neutrinos coming out of the sun. How will I determine?
So for that you have to do the whole calculations of solar dynamics. So mass of the sun, how many hydrogen atoms, how sun evolved from blah blah blah. So this involves lots of input. It involves inputs like metallicity of the sun, what is the fraction of heavy elements in the sun right now. And the only way we know of this is by looking at the sun's surface, right? So you look at these black spots, aurora discharges. From that, you get some idea of the convections happening inside the sun. That's called heliosismology. So you do your calculations, you try to match them with this heliosismological data. If they are consistent, you say, okay, my model is correct, and so on. So this is a very, very large set of calculations. Very few people could actually do this. So John Bekan was one of the pioneers in this, who actually kept on improving his calculations of solar neutrino fluxes for 40 years. And at every stage, people were telling him that you must have done some mistake because we are not observing. So that continues works. So what we do is we just take the calculation that the Bekan has given us and we do that. So then came the super Kamiokande experiment. The advantage of super Kamiokande was that it could determine the energy of it. The bad point was threshold was just 5 MeV. Because if it was less than 5 MeV, then it comes. Okay, now this neutrino interacts with an electron. Because NUI, the nucleus, the cross section is not very large. So basically, it looks at electrons, it comes, hits an electron goes away. This electron can give you a Cherenkov light, that is what we did. See, atmospheric neutrinos, we were talking about energies of the order of G. Okay. So this electron that came out after the neutrino hitting the nucleus, for example, was very highly energetic. So it actually gave out lots of photons, and that was not a problem, determining the shape of the ring. There were lots of these dots that would make up a circle. For solar neutrinos, since the energy of NUI is very low, of the order of 10 MeV, 5 to 10 MeV, the energy of electron that comes out is also about 5 to 10 MeV. Turns out that a 5 MeV electron will only give very few Cherenkov photons. So it's very difficult to reconstruct a circle. So it's only when you cross 5 MeV that you can actually reconstruct a circle. And therefore you can find energy of this neutrino. Therefore, when you want to look at neutrinos from water Cherenkov technique, the minimum energy has to be of the order of 5 MeV. That's why super Kamiokande only starts at 5 MeV. And now you see, this is again data divided by standard solar model. So if you see all the neutrinos, it would have meant that you just get one single line over here at 1. Data equal to standard solar. What you observed was this. So some kind of an up and down thing around 0.4 to 0.5. So this tells you that between 5 MeV and this 14 MeV, approximately half the neutrinos are lost. It also tells you that the behavior is kind of constant. You can also, of course, imagine certain figures here, but then we will do some chi-square fits and find out if there is some kind. We will come to that. Oh, data divided by standard solar model. So no oscillation is 1. So you can see if we reach So this is actually a flat line. You can see some chi-squares here. Chi-square for flat line is 13 for 18 degrees of freedom. So chi-square per degree of freedom is 0.80. So reasonably good. So it's a good fit to flat. Okay, we'll come to that. But it's also a very important feature that in the super Kamiokande, we actually saw a flat line. So you did not actually see oscillations going up and down. You only saw a flat line. That is very important. When we try to figure out what the solution was, we will use this fact very often. That the answer seems to be a flat line. So now at this point of time, we had discussion, right? So we of course saw that gallium, chlorine, and water experiments gave us different results, okay? Different amount of neutrinos and also. So one thing that we wanted to confirm was where did the neutrinos go? In the case of atmospheric also, we saw that we knew they did not go to nu, so we expected them to go to nu tau. So we saw that going to nu tau matches, going to nu star does not. So similar question has to be asked for solar neutrinos. Where do the neutrinos go? So the idea was now to design an experiment which will tell you where the neutrinos went. Whether they actually went to other kinds of neutrinos or whether they went to something else. And for that, the experiment that was done was this SNO. So what SNO had heavy water. B2. So this has basically deuterium nuclei, oxygen nuclei, and electrons. Neutrinos will interact with these three points. These three. Cross section of neutrinos with oxygen is very small. So we just neglect this. In fact, neutrinos with energy less than 15 MeV have almost zero cross section in oxygen. Except energy levels of oxygen, you need at least about 50 MeV. So you are left with deuterium and electron. So let's see what happens when neutrinos interact with deuterium and electron. So let's look at nu E. If nu E combines with deuterium, so deuterium is basically a proton and a neutron. So nu E can do two things. Either it can convert a neutron to a proton, so it makes P, and electron goes up. So that's one thing it can do. Second thing it can do is it just breaks out the nucleus. It does nothing else. So this can simply do P plus N and nu E goes up. Just breaks up. That's what it does. Can you do anything else? Perhaps not. Not that I see here. To see something. Then you have electron and nu E with electron plus electron can undergo scattering, right? Nu E plus electron. That's one reaction. So nu essentially has these three interactions. What about nu? If you have nu, can you have this reaction? And if not, why not? Can I have a reaction? For example, in which mu breaks up the deuterium, so let's say Pn goes to P and mu minus. So what's the problem with this? Mass of muon is large. So if you want to create a muon has a mass of 100 MeV. You must have mu in energy at least 200 MeV, 400 MeV. Our neutrinos have energy of 10 MeV. So in principle this is possible, but we know that this is not inside the sun. Similarly, this reaction, this we can take this. You have Pn, you just break it. This can happen inside us. Second one. So mu plus P going to E, N and mu is possible. Okay. Everyone agrees on this, right? It's a very crucial thing. This doesn't happen, but this happens. This is what is called as neutron current interactions, NC. Okay. Simply because nu E comes out, nu E goes out. So it's a neutron current interaction. So this is NC, this is also NC. So an NC interaction will not be able to distinguish between electron neutrino and muon neutrino. Right. So therefore, if you look at only the neutron current interactions, then it should not matter to you whether a nu E came to you as nu E or whether it went to nu or neutron. The flux you get should be exact the same as the flux you expect. So if your theory is correct that neutrinos have only loss by oscillations, then you must get exactly what you expected as your neutrino. This is something you could not do with water challenge, but you could do it with deuterium. So this reaction is very important. So these two. There's no difference. This reaction, on the other hand, is called charge current, and this happens only for nu. So if you look at this interaction, then you will only see nu E, and you will never see mu and nu. So this is what is called as the charge current increase. The third kind of interaction is this, nu E plus electron giving nu E plus electron. What about mu? Is this possible? Neutral current. It's possible, right? Always happen. Similarly, nu tau can always happen. Okay. So one would say that this also doesn't seem to distinguish between nu E and nu E.
But that is possible both CC and NC.
Right. So, however, there is one difference, which is that if you look at the NC kind of interactions, you have mu, Z, electron. Okay. This can happen for mu and nu tau and mu. All three can be in the position. However, this interaction, which is nu E into electron through charge current, can happen only for nu E. As a result, the cross section of nu E electron is more than cross section of mu electron. Cross section consists of both parts, charge and neutral current. And this cross section is clearly more than this because this has more channels. In fact, it is a lot more. So, rule of thumb is sigma of mu electron is nearly equal to 6 times sigma of mu electron. So, electron cross section is a factor of 6 higher than the muon cross section. you can go back and see what happens inside water. So what about water? So water challenge. So basically water. HO and E minus. Electron nu E interaction with O is 0. H also is 0. So what is actually this electron? So you have, if you have nu E, it interacts with this electron, and it gives you number of events equal to proportional to sigma of nu E times. If nu reach at the Earth, you get number of events proportional to sigma of nu times. And this is 1/6 of this. So if you get a mixture of nu E and nu, then your total number of events is your flux of nu E times cross section of nu E electron plus flux of nu times cross section of nu electron plus flux of nu tau times cross section of nu tau. So what you see here is actually 5 of nu E times sigma of nu E electron plus 1/6 of 5 nu plus 5 nu tau times cross section of nu E. So I just used the approximate relation that cross section of nu with electron is about 1/6 that of nu E. Therefore, now we are seeing three kinds of reaction. This reaction that we saw was nu plus electron giving nu plus electron. This is the so-called ES events. ES stands for elastic scattering. Sometimes also electron scattering. Use it for both. This is electron elastic scattering. This is sensitive to flux of nu E plus 1/6 the flux of nu and nu tau. Because the cross section of nu and nu tau is 1/6. This was for ES. Then we saw this CC interaction, the charge-square interaction, where we had nu E plus deuteron giving you proton, proton, electron. This only measured the value of nu E, because only nu E could interact like this. You can't have nu E. And then we had these neutral current interactions, which were neutrino plus some deuteron giving P, N, and neutrino. And these were sensitive to the flux of everything. So when you had deuterium, E2O, it means you are sensitive to 3 combinations of 5 nu E, 5 nu, and 5 nu tau. These are 3 distinct combinations. Okay. Nu and nu tau always come together, so it's called as 5 nu tau. So this is something that was not allowed to do before. See, when you did radiochemical experiments, you only had nu E. Nuclear reactions have only nu E in them. So radiochemical interactions only measured flux of nu E. So also radiochemical. Gallium and chlorine. In water channel curve, you only measure this combination. So this is also true for water channel. empty water, you could do all these three at the same region. So that is always better. So this is what SNO gave after it measured all of these. So you see this 5 cc, which is the vertical line, which is charge current interaction, sensitive only to electron flux. So the two axes, this is flux of electron neutrino. This is phi mu plus phi tau. So flux of electron, flux of mu and tau mu. So if you look at this charge current interaction, which is this, is sensitive only to mu e, only to phi e. Therefore, you only get this vertical band like this. So it can restrict the value of your electron flux, but not of the other fluxes. Then if you look at this green flux is simply elastic scattering, the electron scattering. So it is a line with a slope of 6, which is cross section. So the flux, it's called phi es, elastic scattering, with a slope of 6, and it goes to intersect this red line. So you expect that the intersection point lies somewhere. The third is this neutral current interaction, which is any neutrino acting on deuterium, split it up into neutron, proton, and some other neutrino. This is a line with slope equal to 1. It's sensitive to mu e plus mu plus mu. So two good things. One is that all these three bands intersect at a point, or intersect in some region. So we are consistent. That's one. Second thing is that this blue band or neutral currents exactly falls between the predictions of solar model. So this phi SSA is the prediction of standard solar model, and turns out that this blue band falls exactly in the middle. This actually confirms that whatever Bajraj was saying for 40 years was correct, and standard solar model was essentially correct. So we did not doubt these predictions. So the combination of these three tells us that actually we had some flux of mu as we predicted, but somewhere on the way they got lost. Details of how they got lost, we'll do it in the next class. Okay, but right now this is the essence. So this was the experiment, this SNO, the one that clinched the argument that neutrino oscillation is the real answer and nothing to do with the sun. Before this result was confirmed, this neutral current result, people still were doubtful as to the solar model. But this is the experiment where not only did you confirm that solar model was correct, you also confirmed that neutrino oscillations were correct. Not oscillation, convergence. So this tells us for sure that mu e went to mu or mu tau. Which combination we have no clue about right now. We just know that that's how it happens. This is one thing I wanted to show you. So a question is, how do we know whether a neutrino that we see is from the sun? Energy is fine. So of course you only look at neutrinos which are energy less than about 20 MeV. Okay, that's one. But you see 20 MeV is standard rate of radioactive decay. There are lots of radioactive decay inside Earth. You have nuclear reactors somewhere around and you can attack around. So one way one would say that, oh okay, so you look at neutrinos that are coming, you see which direction the electron goes, and then you see whether the electron is nearly coming from the sun or not. However, of course, the neutrino is also some MeVs, electron is half a MeV. So electron will go in nearly same direction, but not exactly. There will be some spread, measurement of it. So this shows you what the error approximately is. So if you look at, so of course, assume that everything is solar neutral. Then you try to determine the angle between the direction of the sun and direction of outgoing electron, and you plot this. What you get is something like this. So you see a lot of background. Okay. So you actually see a lot of electrons in the detector which do not come from the sun. They come from other things, radioactive decay, blah, blah. But you then see this nice solar. So this tells you that these neutrinos, which are in this peak, have come from the sun. So finally, you do analysis in terms of statistical basis, because among these neutrinos, some of them are background ones, so you don't know which came from background. Okay. So this is the source of error that you have to take into account when you do solar neutral analysis. This angle is large, so if you look at this cosine theta sun is 0.5. So 0.5 is, cos theta is 0.5. What is theta? 60. Okay. So this is 60 degrees. So these neutrinos are at an angle 60 degrees from the sun. Okay. So the spread is rather large. So this is about 3 sigma, but if you look at the full bit at half maximum, it's still about 30 degrees. So the spread is about 30 degrees. So therefore, if you want to look at the sun and plot neutrinos, you will see something like this. And the center spot, this bright white spot, is about 10 to 20 degrees. Okay, so in some sense, one can say you look at the sun in neutrinos. However, when you look at it in light, it's about 1 degree. Light sun is about 1 degree. Neutrino is about 10 to 20 degrees. But that's not because of, it's not the fault of the sun, it's the fault of our equipment. You cannot detect it. So this is how you look at the sun in neutrino. Hopefully this will get much better as time passes. So this is how we will end today's lecture. So this is a plot which tells you summary of all neutrino experiments. So these columns which are yellow in the left-hand columns. So these are all theory predictions. So green is beryllium neutrinos, yellow is boron neutrinos, red is EB neutrinos, and so on. These are predictions, and these are observations. So chlorine experiments gave us this observation. So about 1/3 of the maximum, as we saw earlier. The water experiments gave us about 45% compared to 1. Cadmium experiments gave us about 60%, maybe also 50%. Roughly 126. Out of this is 50, about 50%. If you look at D2O experiments, heavy water experiments with charge current, give you 30%. And if you look at D2O with all neutrinos, neutral current, it give you about more than 90%. So our aim now should be to explain all these different data by one mechanism. So there should be one mechanism when applied to all these different energy ranges. You should be able to predict all these fluxes. So it turns out that the mechanism involves neutrino mixing, neutrino oscillations, but also an important part of the mechanism is going to be the travel of neutrinos through varying matter density inside the sun. So we will stop here today. And next Monday, we will talk about neutrino.